In the previous video, we saw that the gradient points in the direction of steepest increase of a function. So we've seen that if you have a function of two variables and it's differentiable at the point a comma b, then the directional derivative d sub u of f at a comma b is maximized when the unit vector u is equal to the unit vector that's pointing in the same direction as the gradient. So if you take the gradient and then divide by the length. And we've proven this by using the definition of differentiability. And in this video, I want to give some more intuition behind what's going on. So we know that a function is approximately given by a plane. I'm just going to call it a planar function. I don't think that's typical, but a function whose graph is a plane, right? So f of xy is approximately, at a comma b, it's approximately f of ab plus partial f of x at ab times x minus a plus partial f of y at ab times y minus b. That's the idea behind f being differentiable. And suppose, again for simplicity, that we're looking at the origin and that f of ab is equal to 0. So then we're saying that f of xy is approximately f sub x at 0, 0 times x plus f sub y at 0, 0 times y. And let's call this f sub x at 0, 0 like c1, and then let's call that other constant, this other constant f sub y at 0, 0 c2. So it's basically a constant times x plus another constant times y, right? And then the graph of that is a plane. So, and then the gradient is just c1, c2, okay? So let's try to think about, okay, since our function is approximately this simple function, let's just try to think about what would maximize this simple function. So, for example, suppose that f sub x at 0, 0 is 4, and suppose that f sub y at 0, 0 is negative 3. Okay, then your function f of xy is approximately 4x minus 3y. Okay. So remember that we're trying to figure out, so here's the point 0, 0. And we're trying to figure out what unit vector, so we want to see which unit vector will maximize the directional derivative. Well, if your vector is x comma y, right, then the directional derivative we've seen is just equal to 4x minus 3y, because the gradient of f at 0, 0 is 4, negative 3, and your unit vector u, let's call it x comma y, then the dot product, we've seen that the directional derivative is just the dot product, right? That's 4x minus 3y. So we want to maximize this. So what we're trying to do is we're trying to maximize four x minus 3y subject to the constraint that x squared plus y squared is 1, because your vector is a unit vector. Right. So the intuition, I'm trying to give some intuition behind the result. We know what the result is. We know that it's in the direction of the gradient. So in the direction of 4, negative 3. But we can actually prove this result more directly. So, okay, one way to do this is by Lagrange multipliers, but I'm going to show a more kind of simpler way of doing it. So here's your circle, x-axis, y-axis, and you want to see out of all the points on the circle, what will maximize 4x minus 3y? Well, could it be that 4x, so let's look at the graph of 4x minus 3y equals 0. So the graph of 4x minus 3y equals 0 is a line. It's just given by y equals 4/3 x. Is that right? Yeah, 4/3 x. So if you look at y equals 4/3 x, that's this line. So what does that tell you? What do we know about the intersection points here and here? We know that at these points, 4x minus 3y is equal to 0. This is the line y equals, this is the line 4x minus 3y is equal to 0. So we know at these points in blue, 4x minus 3y is equal to 0. Now what about 4x minus 3y equals 1? Well, that would be 4x is 3y plus 1, and then subtract 1, 4x minus 1 equals 3y, and then divide both sides by 3, you get y equals 4/3 x minus 1/3. So if you look at 4/3 x minus 1/3, that's here. Okay, well, this is not a very good picture, but it's just a line that's 1/3 below the blue line, so something like this. Right? This is going to be 4x minus 3y equals 1. So where this kind of bluish greenish line intersects the circle, at these points on the circle, 4x minus 3y is 1. So at these blue-green points, like the aquamarine points on the circle, the value of your function is actually bigger, right? Because the value is 1. At the blue points, the value is 0. And you're trying to maximize the directional derivative. So at the blue points, the directional derivative is 0. At the blue-green points, the directional derivative is 1. Remember that this is the directional derivative. And so we see that what's going on is that when you look at 4x minus y equals c. So first we looked at 4x minus 3y equals 0, then we looked at 4x minus 3y equals 1. Now we're just looking in general at 4x minus 3y equals c. That is going to be 4x is 3y plus c. So then you subtract c on both sides. 4x minus c equals 3y. You divide by 3. 4/3 x minus c over 3. So it's a line with slope 4/3 x. And then as c gets bigger and bigger, your line gets lower and lower because your y-intercept gets more and more negative. So basically what you're doing is you're trying to see, okay, what happens if I increase c a little? Can I make that happen? Like, is there a point on the circle that intersects that line? So I can make c bigger by moving the line down, basically. So if I have this line, right, this is going to be 4x minus 3y equals, I don't know, something bigger than 1, right? And then I can just, like maybe that's my c1, and then I can make c bigger by making a different c1, like a different c, so c2. And then I just want to keep moving the lines down until I can't move it anymore. Because if I move the line all the way down, like here there is no unit vector xy that I can plug in to find the directional derivative, right? Like there's no xy that satisfies the constraint that x squared plus y squared has to be 1. So the biggest c possible is going to be the line that just touches the circle. This line. This line that just touches the circle at one point. This 4x minus 3y equals c. This c, okay, that is the maximal c I can get. And so that's going to be the biggest possible directional derivative I can get, is this value of c. So the question is, what line is this? What value of c do I have when the line is just tangent? Well, recall that when you have a circle, so this is my unit circle, and you have a line that's just tangent to the circle. Oh, I don't want to make it look like it's a 45-degree angle. Just tangent to the circle like this. This vector from the origin, this radius, right, this line segment from the center of the circle, in this case the origin, out to this line, when your line is tangent to the circle, you get a 90-degree angle. So the question is, what vector is that? Like, what vector will make a 90-degree angle with this line? Well, this line is y equals, let's see, it's y equals 4/3 x minus c over 3, right? So when x increases by 1, well, when x increases by 3, y increases by 4. So this is not the best picture because I was just drawing a general picture. It should be more like this. When y increases by 3, okay, so you're going to have to pretend that this line is steeper than it actually is. When x increases by 3, y increases by 4. Okay. Maybe I should make this line steeper. Y increases by 4. I don't know, something like that. Okay, so that's this line, y equals 4/3 x minus c over 3. So this vector along the line is 3, 4. Right? I have this vector 3, 4 here. So what vector is perpendicular to 3, 4? Well, it's 4, -3. Okay? 4, -3 is perpendicular to 3, 4. Well, 4, 3 is parallel to the gradient, right? The gradient was actually 4, -3. So that explains why the gradient is in the direction of steepest ascent. Because out of all the points on the circle that you can move on, right, all the possible unit vectors, the one that gives you the biggest directional derivative is when you're, it's when you are, when you look at 4x minus 3y equals c, when that line is tangent to the circle, and then you have the direction that's perpendicular to that line. And that's when your vector is the gradient. So that gives you some intuition for why it's the gradient. Another explanation is if you look at parametrizing. So another way to solve the problem is we're trying to maximize 4x minus 3y subject to x squared plus y squared equals 1, right? So another way of thinking about this problem is to parameterize the circle. So we know we're on the circle, so we know that we can describe the points in terms of, say, t. We know that x is cosine t, y is sine t, and then as t goes from 0 to 2 pi, you describe all the points on the circle. So one way to think about this is we want to maximize, so we're trying to maximize 4x minus 3y, but we can describe that in terms of t by 4 cosine t minus 3 sine t. So let's call this function g of t. And now we can just use Calc 1 techniques to do this. Right? So we just take the derivative, g prime of t, that's going to be negative 4 sine t minus 3 cosine t. We set this equal to 0. And then we can add 3 cosine t to both sides. So negative 4 sine t is 3 cosine t. And then we can divide both sides by cosine t to get, and then divide by negative 4 to get the tangent of t is negative 3/4. Well, if tangent of t is negative 3/4, where is that? So tangent is the ratio of opposite to adjacent. So let's see. So like here. Right? If you go 4 units, say 4/5 units here, and then negative 3/5 units here, that's your theta, or your t. And again, that's the direction of the gradient, right? That's the direction of the gradient, 4, negative 3. Of course, divided by 5, which is the length. So Here, maybe I should divide by 5 to make it a unit vector. But the point is that, again, we see that at that point, when tangent of t is -3/4, which is when the gradient, when your unit vector is in the direction of the gradient, that's when you maximize 4x minus 3y. So that gives you another way of thinking. It's kind of the same idea as using this fact about the dot product, right? But no, it's slightly different because the first way we saw this is we saw that 4x minus 3y is the dot product, and then we used this fact about the dot product. But to see why the answer is what it is, we gave 2 additional arguments. One way is to use facts about lines and circles, and then the other way of thinking about it was we used Calc 1 to do it. So these 2 explanations, we didn't use any facts about the dot product, but I hope that this gives you some more intuition about why it's true. So then once you understand that your function, the directional derivative, is maximized in the direction of the gradient in this special case when your function is just a constant times x plus a constant times y, then you can say, well, intuitively, once you understand that, it kind of makes sense that the same thing would be true for a general differentiable function, because your function, if it's differentiable, is approximately given by this planar function, or linear function in 2 variables. And it's true for a linear function in 2 variables, and so it makes sense that the statement would be true in general. So that's how you can get some intuition behind why the directional derivative is maximized in the direction of the gradient. Because you can check in several ways that it's true when you have a function that's simple, that's just c1x plus c2y, and then an arbitrary function is approximately that function. Okay, so that's what I wanted to say about the gradient and the directional derivative.